All right, good afternoon, everyone. Welcome to our colloquium for week 9 of this semester. I'm very pleased to introduce Pantea Pooladvand from the University of Sydney, who will be giving a talk entitled, How Do Viruses Move? Modeling Diffusion of Oncolytic Virus in Collagen-Dense Tumours. Pantea is a PhD student at the University of Sydney, working with Peter Kim. Her area of interest includes modeling tumor growth, virotherapy, and immunology. In 2019, Pantea was awarded Best Student Presentation at the ANSIEM NSW ACT branch meeting and the joint Wollongong Newcastle workshop. With that, thank you again, Pantea, for being here. It's all yours.
Oh, thank you, Justin. Hi, everyone. Thank you so much for inviting me to speak today. And thank you to everyone who's given up their Friday afternoon to join this presentation, this talk. Just as a bit of an introduction into this topic, very early on in my PhD, I was looking at images of virotherapy, and what I realized is that although viruses seem to be a really promising way into tackling tumor growth and tackling cancer cells, there seems to be a real problem with their diffusion. They seem to cluster into regions of low density. So this is what we wanted to investigate. And we were thinking, Peter and I were thinking, well, in order to properly model virotherapy and virotherapy in dense solid tumors, which I'll get to, we need to account for this lack of diffusion. And that's why we decided to look at creating some kind of a diffusion term. So as a PhD student, this is rather a long talk for me. I'm very excited because I have the time to sort of go through and develop the ideas for you. So I have broken this talk up into a 3-part series. So in part 1, we're going to develop a non-Fickian diffusion term to explain lack of virus diffusion in collagen-dense tumors. In part 2, I'd like to show you why this virus diffusion is important and how it differs from the Fickian diffusion that we commonly use. Then in the 3rd part, what I'd like to do is we're going to incorporate this non-Fickian diffusion term into a full PDE model, and we're going to study virotherapy in collagen-dense tumors. All right, so to begin with, before we start this, I would like to give you some of the background. So let's firstly look at the tumor environment. The tumor environment can be broken up into 2 major parts. The first part is the cancer cells, and these are the carcinoma cells that we see in blue. Everything else that you see in this picture is referred to as the tumor stroma. So the tumor stroma is made up of these non-cancerous cells, so cells such as macrophages and fibroblasts. And this sort of gray wiry matter that you see in the background, this is known as the extracellular matrix, or the ECM. So the ECM gives a real support to the tumor as a whole. The ECM is actually very, very important for our normal cells to function. But in this tumor environment, we find that it is really overexpressed. Now in red here, I've written, and it's really just to remind me to tell you that that in this talk, I'm going to talk about extracellular matrix, or ECM, and collagen interchangeably. Collagen is a part of ECM, and certainly not every single study that looks at problems with the ECM is actually is dealing with collagen, but let's use them interchangeably here just to take away any confusions. Okay, so what is the issues with the extracellular matrix? So the ECM, it contains growth factors that support tumor growth. They can physically block therapeutic drugs from accessing sort of the tumor cells. They can add to the pressure within the tumor, and they also support cell migration in later stages. So the part that we're going to be concerned with, and the part that we're going to model later, is this physical block to the cancer cells. Very quickly, I'd like to talk about how the oncolytic virus works as well. So the way that oncolytic viruses work is that they actually normally target tumor cells. So what they do is they will target the tumor cell and they will bind to the tumor surface. Once they've been able to successfully bind, they will then internalize into the tumor cell. And this stage we call cell infection. After infection, the virus will then replicate within the cell and at some stage is going to burst out of the cell. And this last process is called lysis, and this is obviously where the cell dies. Now, this process obviously encompasses a whole bunch of very complicated interactions, but for our model, which I'll introduce later on, these are the processes that we need to understand. So I want to show you just a quick slide that describes the differences in treatment between when you have a tumor that is high in collagen versus a tumor that's low in collagen. So here we have 3 different types of cell lines, so 3 different types of cancers. In this first one with the PBS, so in the 3 graphs where you have the PBS, this is the tumor growing without any sort of treatment. So this is your control groups. This second line, so the line with add E1B, this is a tumor that is growing that's been treated with just a standard oncolytic virus. These tumors are all dense in collagen initially. And then this last one, this add E1B RLX, this is a virus that produces relaxin, and relaxin can actually degrade the ECM. We're not concerned with this process for this presentation, but what I want you to notice is that between the tumor that's been between the tumor that has been treated with a normal oncolytic virus and one that's been treated that contains relaxin, where the collagen is being degraded, there's a major change in treatment. Now, just to get an idea of how that works, here we've got cells and the extracellular matrix. If you inject the virus into this tumor, the virus can pretty much kill and infect the tumor cells in the injection zone, and then the virus pretty much decays away. Now, if we inject this relaxin-expressing oncolytic virus, what it can do is it will infect the cells in the initial injection zone. These cells will then produce relaxin, which eats away at the collagen, and we get a much better infection of the tumor cells. And again, as I said, we're not really focusing on how this relaxin is produced and the dynamics of a virus that produces relaxin. But the idea here is that I want you to see how much better this treatment is once we decay ECM, which tells us that there's a real link between the ECM and the virus spread. Okay, so a little bit about virotherapy models. So conventionally, virus spread in tumors is modeled using a variation of advection diffusion equations. So here, this is the standard Fickian diffusion. If C represents the concentration of viruses, D here represents the diffusion coefficient. This can be a constant, or it can vary spatially, for example. And then we can have this advection term. And the advection term, there's the V here is the interstitial pressure, or interstitial fluid velocity, and then we can have some kind of source or sink terms. We can either have diffusion or have advection or both. So models that actually consider virus diffusion or virus spread as being impacted by ECM are rare, but I'm going to show you a couple of models that use some form of this equation. So this first model by Kim investigates the co-injection of Chase ABC, and Chase ABC is an enzyme that degrades a particular type of ECM in glioblastoma. So for the virus equation, what they have is they have this Fickian diffusion, and this diffusion coefficient is a function of local ECM density. So here we've got that this diffusion coefficient, we have some constants here. This dPBS is the diffusion coefficient of virus in PBS. So this would be the natural diffusion rate of the virus, but that's going to be hindered by the ECM in the local, in a given local environment. So what they're doing is measuring the ECM in a local environment. If it's high, your diffusion constant is going to, your diffusion rate is going to drop. And if it's low, obviously your diffusion rate is going to increase. So this is one type of model where the ECM has been considered for virotherapy. So here's another model where they captured the effect of ECM on viruses by using a taxus term towards ECM gradients. So here we've got a natural diffusion rate again, and then this diffusion is a constant diffusion rate. And we have this taxus term here. And so what the authors want to do here is that they assume that viruses can actually interact with a larger number of cancer cells in regions where ECM is low. So where ECM is low, you have a lot of cancer cells. This is considering that the tumor is quite dense. And so therefore the viruses are going to follow these gradients to where ECM is low and cancer cells are high. Now, both of these models actually were able to capture experimental results really well. But what we wanted to do in this work was actually to try and understand how the diffusion is happening within this environment, as opposed to just modeling the problem. So we decided to take a more mechanistic approach to modeling this diffusion term. Okay, so what we're going to do in part one is to derive a diffusion term that explains virus clusters in collagen. So to do this, I wanted to find some kind of experimental results that captured virus diffusion in collagen. This is a really nice experiment by Macquarie. And what they did was they took melanomas, and these melanomas, as you can see in this domain, there's a high collagen here, and the collagen drops off, and then the collagen's low on this end. So the red is the collagen. Then what they did was they took these non-replicating viruses and they injected them into the center of this space. And they took an image of virus distribution 30 minutes later. And what they found was that the virus had diffused in this region of low collagen, but it was kind of, and there weren't actually many virus particles in the region of high collagen. So they wanted to know whether this phenomena was actually happening because of virus size, or whether there was some other interaction between the virus and the collagen. So what they then did was they took dextrin, and dextrin is, the particles are actually like 100 or 1,000 times much smaller. They're significantly smaller than the virus particles. And what they did was they followed exactly the same experiment. They injected it. Half an hour later, they went to have a look. And what they found was that the dextrin had actually had quite a uniform diffusion through the collagen environment. So their understanding was that, and the conclusion to this was that the virus is actually being impeded due to its size. Okay, so we wanted to take this experiment and use it to find our diffusion term. So before we do that, before we actually use that experiment, what we're going to do to derive our diffusion term is we're going to use a random walk. Assume virus particles follow a random walk upon injection into a tumor. Consider virus V at position X at time t. Okay, so let's say at the next time step, the virus has a chance of moving left or right with a probability of 1/2 in each direction. But now let's assume that the motion of the virus also depends on this Q, this squeeze probability. And this squeeze probability is unique to each position. Now, I'm going to make this squeeze probability a function of collagen, but I will show you that in a couple of slides. To begin with, let's go ahead and use this random walk to derive the Fickian diffusion. So the density of virus the density V of viruses at position X at the next time step, t plus delta t, is, it's going to be, so we're going to lose, it's going to be the viruses that are going to move to the left, the viruses that are going to move to the right, and the viruses that are going to come in from left and right. So the way this works is, to get for Fickian diffusion, we take the squeeze probability, the average of the squeeze probability from the left and the right, and the average of squeeze probability from the left and the center, and from the right and the center for each of these. Now, if we rearrange and using a Taylor series expansion about xt, we arrive at this this term, and we let delta x and delta t go to 0, we can derive the Fickian diffusion term that we are, most of us are familiar with. So let's talk about this squeeze probability. What should the squeeze probability be? Well, let's say if we take the collagen, so let's take C of X, the collagen, as the collagen density over collagen carrying capacity. So it's a ratio of collagen. And let's say that Q of X is some constant K, 1 minus C. And let's just let K be 1. So this is a very simple way to model the squeeze probability. So if we then mimic the environment that we see in the experiment, therefore our squeeze probability would just kind of mirror, would be a reflection of collagen density. So the squeeze probability is high where collagen density is low and vice versa. So we're going to use this to generate virus diffusion. So if we inject a virus, oh, sorry, I don't know why this is, 1 second. Okay, I'll just try and do that again. Okay, so let's see what happens here when we inject our virus. So when we inject the virus at the center of this collagen, what we see is actually the virus will initially spread faster into the region of low collagen density. And this is important, and this is something that I'll be looking at later on, because although eventually we will end up with a homogeneous state, initially our virus will move into regions of low collagen density. So let's now take a look at a different case. So this is case 2, non-Fickian diffusion, and we call this a sticky case. So in this case, the virus struggles to jump out. Virus position at the next time step depends on squeeze probability Q at its current location. So this time, the master equation for the viruses at the next time step T plus delta T is going to depend. So at moving out of position X and coming into position X is going to depend on the squeeze probability at the location where the virus is currently residing. Now, if we follow this again in the same method as before, do a Taylor series expansion, take delta X and delta T to 0, this will again lead us to this diffusion term here. So if we now run this diffusion term, this time, what do we see? We see that the virus will actually preferentially move into regions of high collagen density. And I mean, we can already see that this doesn't really make sense for what we are trying to achieve. You know, we should be getting something that is opposite this. So at this stage here, we sort of don't go on with this model. Okay, so here's case 3. So this is another non-Fickian diffusion case, and this time the virus position at the next time step depends on Q at Q at the adjacent location where it wants to enter. So the master equation this time for the viruses that are leaving position X, their motion into the next into adjacent position depends on the squeeze probability in the positions they're trying to enter, and the ones that are trying to come into position X, their squeeze probability depends on the squeeze probability as position X. Okay, if we again rearrange and use a Taylor series expansion, we end up with a diffusion term that looks like this. So if we now run this diffusion term, and I actually forgot to mention that for these simulations, our boundaries, we have no flux boundary conditions. Okay, so when we run this diffusion, we see that the virus is going to preferentially move into regions of low collagen density. And we can actually even do a steady state analysis and show that this will be its steady state distribution. So this looks like a good candidate for what we're actually trying to do. We can see that the virus is going to diffuse preferentially into that region and is going to stay in that region importantly. So I want to bring your attention to these experimental results again. So we will be looking at this again later on when we look at the simulations from the full model. here we see that we have this sort of clustering behavior. So what are we looking at? There's 3 different cell lines here, 3 different types of cancers that are dense in collagen. This DL-LAC-Z is your standard adenovirus. And if you look where it's been injected in 3 locations. We can see that there's little clusters of infected cells. So the blue are the infected cells. Now, again, if you reduce the collagen with relaxin, you get this much better spread. And so these are just the images magnified. And this is true in all 3 cell lines. We see clusters over in this one. Here we see a good spread of infection. So again, we see this link between collagen density and virus spread. So do we see that if we now use our little model here just with virus diffusion, and this is a more heterogeneous collagen distribution, yeah, we start to see these kind of clustering behavior coming through. So as I said, this seems like it's a good candidate for what we're trying to achieve. So a good candidate for our virus diffusion. The question is, though, how much of a better candidate is it to Fickian diffusion? Because in the Fickian diffusion case, we do see an initial movement of the virus into low collagen regions. So, how much better off are we to use something that's probably, a little bit more complicated? Okay, so this takes me to part 2 of the presentation. Okay, so the first thing I want to do now in order to compare Fickian versus non-Fickian is to actually give you a model. So the model we're going to use is this one. Here we've got the uninfected cells and the virus, and they're going to interact at rate beta, and beta UV is going to give us infected cells. Now, the infected cells can also be infected by more viruses. So you can lose more viruses to already infected cells at rate beta INV. The cells that are infected, they're going to go through lysis at alpha delta II. Now, the virus is also going to decay. I don't know why virus decay is so big, but let's just go with it. And that's going to happen at rate delta V. And then the tumor grows logistically, and we also have this collagen. Now, I've put this in just to show that the collagen can suppress virus diffusion. Okay, so having a look at the model. Now, there are many ways that models like this can be formulated, but in this case, what we have here is we have these uninfected tumor cells. They have a diffusion rate, just a normal standard Fickian diffusion rate, and we have growth. Now, in the case of growth here, what I've done is the growth is logistic and does depend on the density of uninfected cells and infected cells. But the growth is also suppressed by collagen in this model. Now, this then assumes that, I guess, if you have a tumor that is invasive, this would assume a relatively kind of young tumor where the collagen is able to suppress it. And then we have this beta UV, which is the cells that are lost to virus infection. Now, here with the virus density, we have the this new virus, non-Fickian virus diffusion, and we have new viruses coming on due to lysis, and here we have the viruses lost to infection and just virus decay. Infected cells are going to diffuse. There's going to be new infections coming on from you, and then there's going to be cells that are going to lysis, and that's going to feed back into the virus population. Now, importantly here, this is the full model for collagen density. But at this stage right now, our CT just equals 0. But I just wanted to show you that you can have this full model down, where the collagen is also changing in time. It's growing, it's diffusing, and so on. But for these simulations that we're going to have, the collagen does not change in time. Okay, so over here I've put in the squeeze probability. This K is actually just equal to 1. Importantly, beta. Beta, which is the infection rate in this model, is dependent on collagen density. So as collagen density increases, infection decreases. And this makes good sense to me, because if the collagen is shielding cells, there's a good chance that it's going to stop infection. Okay, so let's take a look at what happens if we compare. So just to make it clear, the non-Fickian is this virus diffusion. In the Fickian case, we just have the Fickian diffusion rate that we saw earlier. So what happens? Let's take a look at this scenario here. So here we've got the tumor cells. Well, let's say that there's a collagen well. So this pink here is our collagen well. And within this well, we've got tumor cells. And we inject the virus directly into this region where the tumor cells are. The Fickian virus in 10 days and the non-Fickian virus in 10 days. The Fickian virus has actually spread out into regions of high collagen density. The non-Fickian virus has remained within this region. And then in 3 months, the Fickian virus has diffused out even further. The non-Fickian virus in 3 months has remained within this well, and we have a lot of infection in this well. So this is a relatively, the tumor growth for these models have been fitted to mice models. So they're actually quite aggressive types of tumors, because tumors in mice tend to grow pretty quickly. So the tumor growth rate here is actually quite high. So what do we see? Well, if we compare the percentage of infected cells and the tumor population between the two models, in 180 days, what we have that the non-Fickian virus actually has a lot more infection than the Fickian virus. In the same way, the tumor population the non-Fickian virus is able to reduce the tumor population compared to the Fickian virus. So we see these differences in results in this case, where the non-Fickian, it seems here that the Fickian virus is actually underestimating tumor population size. Overestimating tumor population. Okay, here's another case. So in this case, what we have is we have a collagen well again. This collagen well doesn't have any cells, it's devoid of cells to begin with, and all the cells are out here in the collagen. So these are like little wells where there's no cancer cells in there. If we inject the virus into these regions, what we see is that the Fickian diffusion in 3 months, well, it's pretty much reached a homogeneous state. The non-Fickian virus, it's still concentrated majority of in the well. There's a little bit on the outsides, but that's because this collagen well is not completely full. And so what we see is that percentage of infected cells, there is an the Fickian case considers that there's a higher amount of infection compared to the non-Fickian, and vice versa for the tumor population. Now, the results in this case are actually pretty small, but what we need to consider here is 2 things. The first thing is that I have let the virus infection rate beta depend on collagen density. So that will also be impacting the results here. The second thing that we need to take into consideration is this is just a single collagen well. In a tumor, there would be many, many of these collagen sort of little wells. And then these results would actually just, I guess, they would add up to a much larger error. Okay, so now that we've considered the 2 different types of models, we can have, as I said, the Fickian version or the non-Fickian version. Let's take this non-Fickian diffusion term, and let's take the model and apply it to a 2-dimensional version of the model to see if we can see the kind of spatial results that we get experimentally. And also, I wanted to learn a lot more at this point about what is happening with collagen and how it affects tumor growth, virus treatment. So firstly, let's compare the model to experimental results. So again, here's the picture of the virus in dense collagen to begin with, just to compare. I've set up this two-dimensional model. This is the same set of equations, but I've set it up as a network ODE. I quite enjoy working in this way with this model, just because it gave me a lot of flexibility and a lot of room to move. So if the way I've done this is these just a bunch of random Gaussian functions. If we look at the collagen, the collagen sort of formation, I've sort of taken this from something like this. So if you look at this, this image on the bottom of the page, the blue represents the ECM or the collagen in the surface of this tumor. So here I've tried to sort of mimic that kind of environment for our collagen. This is our uninfected tumor population at the top. Now we inject the virus into 3 locations, again mimicking what the experiment has done, and to begin with we have no infected tumor cells. The densities go from 0 to highest up here at 1. So if I just quickly run this just to give us the idea of what it's going to look like, we can see that we're getting these infections very similar to what you would see in this scenario here. Okay. So this is really my interest at this stage when it comes to this, to modeling these type of problems. As you can see here, I've taken these images, and I really wanted to, well, I didn't take these images, but I've taken these images from a paper, and I really wanted to show you guys the kind of environments that we can, that can happen within a tumor. So you can see here, this is a normal pancreas, and here's pancreatic cancer. And here's lung cancer and breast cancer. And you can see that the formations of collagen, where collagen's blue, and cells are the browny red, is really, really different. And it's really unique to each, not to each, even just to each type of cancer, but to each kind of patient. So I guess the aim of the project from here moving forward is, can we predict how a patient is going to respond in relation to this sort of, configurations of collagens and cells? And that's really the big idea. I found some data as to the maturation of stroma or maturation of collagen in colorectal cancer and patient survival. So what they've done here is they've actually noticed that depending on the maturation level of the stroma in patients, they can actually predict patient survival. So A in this case, even though it's intuitive or counterintuitive, A is the best type of, I guess, collagen formation you can have, which they've called mature. Then you have this intermediate phase and you have this immature phase. So in the mature phase, we can see that they're kind of like longer and more stringy. And in the intermediate phase, they're becoming more like into these clusters. And here it is in the mature case. And if we look at this probability of survival, we can see that there's a significant drop between mature to immature. Okay, so let's take a look at some of the relationships between cells and collagen and see what we see within our model. At this stage, it is very exploratory. So let's look at 2 tumors that are the same size, but different cell to collagen ratios. So here, this is low collagen, high tumor cell count, and this bottom one is high collagen, low tumor cell count. So if we run these two, let's take a look at what happens. So we can see that initially our tumor is killing the uninfected cells. In this case up here, our virus is growing, it's able to infect. As I said, the collagen isn't changing, it's just there to make sure that we can see the formation of the collagen. In the case on the bottom where we have high collagen, we can see that the virus is not great at infecting in the same way. The virus infection is, staying within little local regions, and the infected cells are also obviously within that region. So if we look at the actual results from this, so tumor outcome with variations in tumor collagen density. Here we've got the same size tumor. So tumor 1 with low collagen, high cell count, tumor 2, high collagen, low cell count. So we can see that the virus obviously, thrives in the low collagen and decays away in high collagen infected cells in the same way, more infection in low collagen than high collagen. And then the percentage of infected cells, the percentage of uninfected cells, in both tumors, initially the tumors are actually decaying away, but in high collagen, the tumor seems to be recovering, whereas in the low collagen, it continues to decay away. However, if we did the same experiment with same size tumor, with the same tumor cell count and different collagen densities, we see slightly different results. So here in this set of experiments, we had the same amount of tumor cells. One has high collagen, one has low collagen. So similar results in virus population and the amount of cells that you're able to infect. But because the tumor in the low collagen is not being suppressed by collagen, it's actually able to grow. So this tumor is able to grow before it actually begins to respond to treatment. And even at day 90, we're still nowhere near where we started. And this is actually something that's been observed in pancreatic cancer. So in certain types of pancreatic cancers, if your stroma is relatively benign, stromas like this where they're not communicating with the cells, this sort of behavior has been observed. So it's not necessarily always a good thing to have a low amount of collagen. Okay, I also wanted to investigate, so that was cell collagen ratios. I also want to start investigating how the size of the deposits, collagen deposits, and whether you have these kind of like long string, these kind of like smaller bits of collagen cells versus larger clusters of collagen cells would change the results. So I ran some simulations to have a look at this. And it looks as though when you look at the images, I'll just stop these, it seems that we are, visually we're getting very different results. So it seems that in the uninfected, with the smaller collagen deposits, we seem to have these kind of viruses that are in smaller clusters. Here it looks like it's, you're getting much bigger virus growth and infected cells. But when I actually then went and looked at the results, this is what I got. So I should mention that in all those cases, you have the same amount of sort of collagen. It's just that it's distributed differently. So if you have small deposits versus large deposits, so this is for the two that we just looked at here, the infected cells, they're roughly around the same amount of infected cells in the 90 days. And then the percentage of the tumor cells, this one looks like it's growing a little bit faster with the small deposits rather than large deposits. But then I thought, okay, I could try and just simulate. I did 6 simulations with different variations. So I different variations of the small deposits and then different variations of the large deposits. And when we look at these results, there's not actually that much difference between the outcomes. Yes, in this case we have we have a little bit of difference in the tumor size, but overall the dynamics hasn't changed. So it seems that at this very, very basic level of exploration, the configuration of the collagen doesn't actually change how the response to virotherapy, what the outcome to virotherapy is. I forgot what I was trying to say there. Okay, let's take a look at these gaps in collagen. So I was also thinking that just as we were talking about the wells before, and I was putting the virus and the collagen in the little wells, I thought, well, most probably, if you're looking at a tumor and this kind of environment, it's probably not going to be smooth. It's probably going to contain these gaps of collagen. And I wanted to see what happens if you have like a small number of gaps or if you have these kind of larger numbers of gaps. So if you run this, let's see what we get. So in the case of small gaps, The virus, although it's kind of hard to tell here, the virus actually spread better through the tumor. And you've got these kind of concentrations of viruses. And this is because, as we saw in the one-dimensional cases, the virus will actually go into these regions of low collagen density. So it goes into these regions and it infects those cells, which is why those regions are highlighted so much with infected cells. Now, in the case of the high college of large number of gaps, the virus will actually even more so fall into these gaps and infect cells into these regions. So we have a lot of infection, but this infection is within these gaps. And what that means is that then the tumor outside, the tumor range that is outside of these gaps can actually continue to grow because the virus has actually become trapped within the gaps. So then if we have a look at the results for this, what we actually find is between no gaps to the large gaps. So this here is the large gaps. It's just come up a little bit funny on that key. So with no gaps versus large gaps. So in the large gaps, the virus population is growing. But as I said, this virus is actually, it's growing within these gaps. These tumors are growing very, very quickly. And that's because, as I said, we've modeled them against mice data and mice tumors just grow quite quickly. Now, if this wasn't the case, I would say that my feeling, and I will check this when I run these simulations again, is that the virus population, if we had a slow growing tumor, the virus population would not grow this fast when it's trapped in these large gaps. Now, the percentage of infected cells, again, because the virus is growing, infecting a lot of cells in this region, it's able to, we just get more infected cells because the virus is growing. However, for the tumor population, we can see that when we have these large gaps, because the virus is falling into these gaps, the tumor will actually continue to grow before it begins to respond. Whereas the smaller gaps or no gaps, you're actually getting a decay pretty much immediately. Okay, what do I have left to show you? So this is probably the most recent work that I've done on this. And I have to dig a little bit deeper here, but I really wanted to put this in and show you. So I did a sensitivity analysis with all the parameters, and I've just grabbed a couple of the parameters to show you. But collagen density, I wanted to see whether collagen density alters the sensitivity of the model to parameters. And in fact, it actually does. And of course, not in every parameter, but I want to show you a couple of parameters here. So here we've got the relative change in tumor cells from some chosen value. In here, we've got the relative change in infected cells. And the parameter that I'm showing you here is the tumor growth rate. So if we perturb the tumor growth rate, if the tumor growth rate is slower than the one that we chose, so if we reduce the tumor growth rate, we see that in low collagen, the virus, sorry, I can just hear something in my microphone. Yeah, so what we see here, if we perturb away to the left to lower values of tumor growth rate, our results change. The results of tumor cells change. And sort of unintuitively, if we actually increase the growth rate, a tumor also responds to treatment better. Now, the same, for the infected cells, so for the same thing with growth rate in relation to infected cells, what we find is that for high collagen, the cells, there's not really much of a change. The system isn't very responsive to change in tumor growth rate. However, the system does respond more to when it's in low collagen to changes in growth rate again. As one last set, I just wanted to show you this one. So here we've got the same I actually didn't mention that this is on day 30, so I'm very sorry. I actually took these measurements on day 30 and compared them. So again, the relative change in tumor cells, and now this is for the change in virus clearance rate. So in high collagen, changing the virus clearance rate doesn't really change the tumor size. However, changing this virus clearance rate in low collagen does change our tumor size. It reduces our tumor size at day 30. Now, same sort of a thing with infected cells. We actually see completely different results in this case. So my point in showing you this, I mean, is just to say that it's important to take this collagen density into consideration in this type of models, because it can impact your parameters and how your parameters actually, how your system responds to its parameters. So in conclusion, I want to say to accurately model viral therapy in dense tumors, cell stroma configurations need to be considered, not just in relation to tumor growth, but also for its influence on therapy. Importantly, where I'd like to go in the future is that modeling this relationship could uncover patterns that assist in predicting patient response to treatment based on a patient's individual cell stroma histology. Thank you so much for your time today.
Thank you, Pantea. That was a very interesting, very informative talk.
Thank you.
If anyone has any questions for Pantea, please feel free to unmute yourself.
I can't see the chat.
Sorry, I'm just trying to. I did have actually a question of my own, if you don't mind.
Please.
So you had 3 models of like diffusion, like you had like the like where you were picking different cues.
Yes, I'll go back. Yeah.
Yeah, and they all seem kind of similar, but like they actually produced, like one of them at least produced results that almost didn't make any sense, right? Because it was going into. So like, is there like a physical intuition as to what's going on there? Like, because you would expect that it wouldn't make that huge of a difference, right? Where you pick.
Exactly. Yeah, which is why I thought that thinking about it in a more mechanistic way kind of made more sense to me. Exactly. So in case 3, which is the one that I said that we like and we've chosen to go with, this is the one that goes and stays in regions of low collagen density, which, you know, makes sense. You know, the virus makes this decision and moves to regions, you know, depending on Q. So if Q is higher in adjacent locations, it's going to move to adjacent locations. But yes, you're right. The one that is the sticky case is almost feels a little bit unintuitive, which is the one where, the virus, where the probability of virus motion depends on where it is. So I guess I was thinking about how this one works, and that's why we decided to think of it as more of a sticky case. Yeah, it definitely feels unintuitive, but yeah, with such a small change, it makes a massive change in the diffusion of the virus. Thank you for your question, Justin.
I did actually have another one. I know I'm kind of hogging it, but like
no.
if anyone else has any questions, please go ahead and ask.
This is very good for my PhD, Justin, so please ask away.
I was actually wondering, like, why so you had the tumor cells diffusing just regular diffusion, right? With
yes.
Why is it that they diffuse so differently from the virus?
Oh, well, okay, so yes, at this stage, I didn't want to put in too many things that are going to complicate the model. I thought about just the tumor cells, as in the tumor cells are not really going to care about the diffusion. They're not really going to be impacted by the diffusion of the virus because, you know, they're so much larger than the virus that they're just going to diffuse out into space where they have space. But I mean, yes, you know, there's a lot more that can be done there. You can also have the diffusion of the tumor cells depends on collagen, which is what I've done with the growth. So yes, that's definitely something that could happen and probably does happen. It probably wouldn't move into regions where it can't go. Yeah.
Thanks. Does anybody else have any questions?
So I don't have any questions per se, but I just wanted to thank you for a great talk. It's a very interesting work you've done, and some good pulling together of various different models to put it together. So thank you.
Thank you so much. Thank you, Catherine. Thank you.
Thanks, Catherine. Any other questions or comments? No?
And I just want to say, Justin, if anyone does have, please feel free to email me, send it through. I would love to chat to anybody else who's working on problems in this area. As I said, I'm just finishing my PhD, so it'd be wonderful to chat to anyone else who's interested in this work.
Great. And I should also mention she just submitted her thesis, so we should all cross our fingers for her.
Thank you.
But yeah, thanks Pantea for a great talk, and it was a pleasure having you here.
Thank you so much. Hope to see you all soon.
Thanks everyone.
Bye. Bye.
Thank you. Yeah.